Good evening and welcome to another episode of Maths in an Empty Classroom with me, Mr. Sutton. This is part one of the first lesson on differentiation using the chain rule, and in this video I'm going to introduce the chain rule and give you an explanation of how it works. But this is going to be quite a audience participation based video. I'm going to get you to do things, pause the video a lot, the idea being you try and discover a lot of this for yourself by working through this process. So what I have is I've put two polynomials on the board, but they're in factorised bracket form, and I want you to do the following three things with each of them. I want you to expand them, then once they're expanded I want you to differentiate them, and with your differentiated result I want you to factorise it as much as you can. Right, so pause the video, do those three things with each of these two functions: expand, differentiate, factorise, and see what you get. Pause. Okay, right, looking at the first one then. So hopefully first thing you did was expanded it out and got y equals x squared plus 6x plus 9. And then when you differentiate to find dy by dx, you get 2x plus 6. And then when you factorise that as much as you possibly can, you would get 2 bracket x plus 3. Okay. Second one, y equals x plus 1 all cubed. When you expand that out fully, you get y equals x cubed plus 3x squared plus 3x plus 1. When you then differentiate that to find dy dx, you would get 3x squared plus 6x plus 3, which can be written as 3 lots of x squared plus 2x plus 1, which can be written as 3 lots of x plus 1 squared. And what I want you to think about is, what is the relationship between what we start with for y and what we finish up with for dy dx? Similarly here, what we start with for y and what we finish up with for dy dx there. Now what I'm just going to do, I'm just going to clear this and just state the result for dy dx underneath each of the initial questions, because we're going to do another couple with an idea of pattern spotting, because you may think you've spotted a pattern already, but inevitably it's not an absolute surefire winner. So we had here dy by dx equals 2 lots of x plus 3, and we had for this one that dy by dx equaled 3 lots of x plus 1 squared. Right, two more for you to try. The first one is y equals 2x plus 1 cubed, and the other one is y equals x cubed plus 1 in a bracket all squared. And again, what I want you to do with each of them is expand it, differentiate it, factorise as much as you can. Pause the video, give it a go. Okay, so expanding this one out, we should have got y equals 8x cubed plus 12x squared plus 6x plus 1, which when we differentiate to find dy by dx, you get 24x squared plus 24x plus 6. Now, thinking about factorising that, you would have 6 lots of 4x squared plus 4x plus 1, which is 6 lots of 2x plus 1 all squared. Infuriatingly close to the pattern that you've seen, perhaps a little bit different. Let's just have a look at this one. Expand it all out, we get y equals x to the power 6 plus 2x cubed plus 1. Differentiate it, we'd get dy by dx equals 6x to the power 5 plus 6x squared, 1 differentiates to, nothing's constant, which would give us, fully factorised, 6x squared, and then in a bracket, x cubed plus 1. Right, as I did before, I'm going to erase the working and just write the result underneath the original question. So we've got y equals 2x plus 1 all cubed, and that differentiated to give us 6 lots of 2x plus 1 squared. Similarly, y equals x cubed plus 1 all squared, we ended up with dy by dx equaling 6x squared lots of x cubed plus 1. Now let's think about patterns. With this one, you may have just thought, oh, this is all right, this is just like normal differentiation. Power comes down and 1 off the power. So the 2's gone to the front, 1 off the 2, 1. Okay. Same thing works here. Power down, 3 down, 1 off the power, 3 lots of x plus 1 squared. And that doesn't work quite so well here. So let's just have a look. If we've done power down, so 3 lots of 2x plus 1 squared, we've got 3, and we wanted 6. So we would have had to multiply it by 2. Just leave you to think about that bit. Similarly here, if we tried the whole power down 1 off the power thing, we have 2x cubed plus 1, get to the power 1. I'll write it for the purpose of seeing that you're reducing the power by 1. But we didn't get 2, we've got 6x squared. What would we have to multiply 2 by to get 6x squared? What would have to be 3x squared. Where's this 2 coming from? Well, it's coming from differentiating 2x. And where's this 3x squared coming from? It's coming from differentiating x cubed. So technically, if I go back to the first ones, x differentiates to 1. So multiply it by 1, it just hasn't changed the result. And similarly here, x plus 1 differentiates to 1, so multiplying by 1 hasn't changed the result. So, how I always like to write this with the chain rule is you power down, you take 1 off the power, and then you multiply it by the differentiated bracket. And what that looks like is if you have y equals a function of x to the power of n. So in each of these examples, a function of x is just something with x. So in this case, it's x plus 3 to a power. So this bit is the function of x. Here, x plus 1 is the function of x. Here, it's 2x plus 1. And here it's x cubed plus 1. So, to find dy by dx, we power down, so n goes at the front. The bracket bit stays the same, as it did in all these examples when we differentiated. 1 off the power, and times by the differentiated bracket, so using f dash x for differentiating this bracket, because that's what we're doing in this case. The two better examples for it are these two here. Power down, so 3, bracket stays the same, 1 off the power times by the differentiated bracket. You see it even more clearly here, x cubed plus 1 all squared, power down, 1 off the power multiplied by the differentiated bracket. Okay, join me in the next video where I'll go through 4 examples of how to do this with other functions. See you then.